Hello. Hello, Lucia. Hello, Pankaj. Is this your regular streaming time? No, not really. I usually stream a little later. Cool, I couldn't solve this daily. Yeah, that's why I wanted to explain my solution, because it's not an easy one. And I have a solution that it's based on a well-known problem. You code in Python? Yes, but sometimes I do C++ as well. Smart coder, welcome. Sometimes I do CPP, C++, or other languages, but usually like Python is my go-to. How do I learn Python? Well, LeetCode is a good way. Where do I learn it? So you can find some tutorials to just to learn the basic syntax, and then I think LeetCode is a good way. So you start doing easy problems, and you can check solutions from others to learn some tricks and the standard libraries. Hello, Verus. How's it going, Verus? I know the essay in C++. Well, that's great. Yeah, I mean, it's pretty straightforward. This one isn't a medium. It's really a hard. Yeah, I agree. So I already knew this problem. That's why I was able to solve it. So I'm gonna explain. So let me first read it for if you haven't already. So minimum height trees. A tree is an undirected graph in which two vertices are connected by exactly one path. Any connected graph without simple cycles is a tree. This is something that you may already know. Given a tree of n nodes labeled from 0 to n minus 1, and well, we have the edges. There are you should know that there are always n minus 1 edges on a tree. So yes, this is the usual way in which we are given a tree. And it says, so it's not rooted. You can choose any node of the tree as the root. When you select a node X as the root, the result tree has height h. Among all possible rooted trees, those with minimum height are called minimum height trees, MHTs. Return a list of all the MHT's root labels, and you can return the answer in any order. The height of a root tree is the number of edges in the longest downward path between the root and a leaf. All right. So here we have an example 1. Hey, xproof, how's it going? Here we have example 1. So this is there are 4 nodes and 3 edges, and here we're shown like all of the 4 nodes could be the root. So here so here 0 is the root, and these are the leaves, and here the height is 2, and here if the root is 1, then the height is 1. And in these 2 cases, yes, I do the contests, and I've been doing the contest streams, so you can check them out. I still have to do the one for the last contest. I'm gonna be doing that in the next days. Anyway, so here the height of these trees when 2 and 3 are the roots, it's 2, so the minimum height is 1 and there's only 1 as a root. Do you do virtual contests? I participate on the contest. All right, so, and here's another example. Here's another example. In this case, these 2 are the minimum height trees. When we have 3 as a root or 4 as the root, they both have height 2. So let's go to the drawing board and let's think about this a little bit. So the way I solve this is with a technique. So let's say that we have let's root the tree from node 0. It doesn't matter from where. Let's say this is node 1 and this is node 2, and maybe here we have something like this. I don't know, let's say that we have this tree. So the way we're gonna handle this is we will first, so let's say that we want to figure out, to calculate what the longest path from each node to any other node, right? Because that is the height of the tree that is root at that node, right? If, for example, if we want to find here let's consider this node. So we want to find the longest path that starts at node 2 and goes to any other node. Okay, and we can break that down into two possibilities. Why is this not changing? Okay. So we're gonna break it down into 2 parts. One is going to be finding the longest path that starts at node 2 and goes to any other node in the subtree rooted at 2, right? So that is easy. That we can do with a DFS. We just find the longest path from our children, and the longest path for 2 will be the maximum of the children plus 1. Okay, and then we want to find the longest path that goes first to the parent, right? And goes to one node in the rest of the tree, outside of this subtree. So notice that once we have, how do we do this? Okay. So first we go up to the root, right? And then from the root, we again have 2 options. We either go up, one option is going up, right? But the other option is going down. But the problem here is that going down, if we find the longest path starting from 1, but going down, maybe we go back down to this node, right? Because so let's start writing down the things that we want to calculate. Why is this in work? Okay. So let's call this down. From starting from 2, the length of the Longest path, we know that it's 1, 2, right? This is 2. And then we want to calculate app from 2. We don't know what this is, but for that we go up to 1, and so we know that down of 1 is 1, 2, and 3, right? Is 3. But notice that that is not a valid path, right? Because we're going to 1, and then we're finding the longest path starting from 1, which goes back to 2, and then goes here, and then goes here, right? But that's not a valid path. We're repeating nodes. So what we're gonna do to handle that is to get, in addition to down, we're going to compute a second downward path, which is going to be the second longest that goes to a different child, right? So here, for example, the down, the second down of 2, in this case, is going this way. So this is going to be 1. Notice that it is less than the first down of 2. And so that means in that way, we're going to find this path. We're going to find, when we go up to the parent of 2, we're going to find the down 2, which is this way, right? And so down prime of 1 is going to be 2, right? And but that path we can use. So finally, the app here, the app of 2 is going to be either the app of 1, right, which is 2, or we want the maximum, or the down prime of 1 plus 1, right? Yeah, and this is also plus 1 because we first go up one edge, and so the app of 1 we know is 2, so this is 2 plus 1 is 3, and the down is again 2 plus 1, and this is the maximum, and so this is 3. So let's check out the code. So let's first create the, let me make this bigger. Let's first create the agency list. So we go over all the edges, we add them, and now we first are going to do DFS to find the first down path and the second down path from each node. So let's call this DFS1, and we're going to be at a node, and we want to know the parent of that node, and we go over all the children, and And now we solve the children, and we want to know if the first down path of the children B plus 1 is greater than our current down path, the longest down path so far. Well, that means that we have to update both. We have to, so now the first down path of U and the second down path of U is going to be updated. So this is the new longest path, and the previous longest path now is the second longest path. This is a typical code for finding the two maximums, and here is the best down path to my child. It's greater than the second one. It's not greater than the first, but it's greater than the second. Then we only update the second path. Okay, so that's it. And now we want to do a second BFS where we are going to compute the app paths. So we want to compute the app path, and again we go over the children, and here we want to make sure, but because this is the other way around, we want to compute the app of 2, so the longest path that first goes up from U, but we want to make sure that we already computed that for the parent, right? So before we do the recursive call, which is going to be this, before we do that, we need to make sure that we compute this for the current node. Okay, so this is going to be the app of B is going to be either the app path of U, which is the parent, plus 1, or now we want to see if the first down path from the parent is equal to the first down path from the child plus 1. In that case, that means that the longest path down from my parent goes through myself, and in that case I want to consider the second best, so down 2 from my parent plus 1. Otherwise I want the down 1 from U plus 1. And that's it. Now we have to call them from the root, and then we have to go over, we want to get the minimum height. So the minimum height is going to be, so the height is for node U now is the height up, the maximum between the longest path that goes up and the longest path that goes down. And now we want to return all the nodes that have, again, the height equals to the minimum. Okay. And that's it. Cool. So here's my submission. Do you have any questions? I don't know if this was clear enough. I think it ended up a little complicated. Cool. Did you follow this? How we define the down one? It's complicated. I got lost. I used the leaves to top. You got lost in some parts. Do you want to be more specific? I can review it. I can go over it again. So you follow this idea of going. So we focus here on solving, so getting the maximum path. Yes, the down paths are through different children, exactly. So that's why here we have two options. So if the current children, the path from the current children is greater than the best so far, the first down path, the longest down path, then we put the new one as the best, and we put the previous best as the second one. So, and that's from a different child. So that's why, yes, the downward path go to through different childs, through different children. And that's why, and here's how we check if the down path. So we always look at the best path from the child. Right. We don't care about the second path from the child. We only look at the best the best path from each child, the longest path from each child. And here, this is how we check is the down path from our parent. So remember that U is the parent of B. So we want to know is the best down path from our parent go through B, through the child. And this is the case where it goes through. And in that case, we use the second down path from the parent, but otherwise we get the first down path from the parent. Do you follow now? Do you think you can reproduce it? I think I've seen simpler solutions. I'll have to check them out. But yeah, this is a technique that comes up in other problems where you do this break into two. The paths that first go down, that go down and the path that first goes up. So you break it down into a subtree and the rest of the tree. So it's beneficial to learn this technique because you can use it to solve other problems as well. So this is how I illustrated the technique. So here from 2, we have down 1 of node 2 is going to be this path, right? It's going to be the path that has length 2. So this is 2. And then down 2 of node 2 is 1. Because we already went down to this child. So we go down to another child, right? And then this is 1. But now we want to know what up of node 2 is. And for that, we go to the parent and we have 2 options. We go up to the parent and then we go up again. And so that is up of 1, the parent, plus 1 because we move up first. Or we cannot go to the longest, to the down 1 of our parent because that's going through us, through node 2. So here we go down 2, the second longest path, 1 plus 1 because again we moved words to get to our parent. And this is the maximum of 2 plus 1 and 2 plus 1, so it ends up being 3. So is it clear now? So again, it's good to, yes, thanks. Okay, got it. So again, it is good to know this technique. Because yes, you could use it for many problems. All right, so that's it. I wanted to go over the daily. So that's all I have. Let me know if what's the technique? Rate path. Okay. Yeah, the technique. I don't know. I think it's called. I heard the name rerouting. So user code guide longest or tree DP. It's called go down the tree. No, well, it's so here's there's tree matching. No, I think there was a DP on trees. I attempted the daily but got TLE. So it is a DP kind of method. Yes. ChatGPT recommended topological sort. Yes, you can do topological sort, but you don't need. I mean, doing recursion, you're already going over the nodes in topological order. But yes, it is DP in the sense that you have a recursion. You're using you're computing values for a node based on the values, the subproblems of its children. And here for its parent. So yes, you could say it's DP. All right, so yeah, okay, let me rate path. Not that he's famous path, so I don't think he needs it, but let's do it. Thank you guys for watching, and see you in the next one. The contest stream I'm gonna be doing. Thank you, Biruz. See you, Lucia. Bye bye.